I know you're really going to enjoy it, so I want to jump right in. So let's just talk about this. One major difference between 2D and 3D visualizations.
Well, I feel like
go ahead.
well, 3D is more. I don't know. I feel like it's more like realistic in a way.
Yep.
And
Way to put it. Okay.
2D is more flat, you know. And with 3D, they have like 3D animations and stuff. So.
And that's exactly what we're going to get into today. So, and how we can make it real. All right. So let me get to the lecture, and you have, obviously you have access to this too, and I highly recommend that you have the slideshow open because there are links in here, and I want you to be able to follow those links. I want you to be able to play around with the examples that we're going to go over. So this section is all about three-dimensional visualizations. And just a reminder of what we mean by a visualization, it's using any sort of interactive or sensory representation that can be, it's attached to this week's assignment. Ayana. Google Slides? It's a Google Slides, not an AirPod. Do you see it?
Yep, I see it.
Okay.
Sorry, I missed it.
And it helps us to learn, right? But 3D visualizations don't just help us learn, they entertain us too. And that's the big part of today that I think is most fascinating.
Hi, I'm Daniel.
Hi, I'm Martin.
Hi, I'm Fernanda. Machine learning is pretty complex, so we've been experimenting with ways to visualize what's happening. There's a core concept in machine learning called high-dimensional space. Here's one way to wrap your head around this concept. You can think about people as being high-dimensional. For example, take famous scientists. You can think about when they were born, where they were born, their fields of study. Each of these is like a dimension of that person. These dimensions become difficult to untangle when you think about different people, because someone might be similar in some ways, but very different in others.
But this is the kind of thing you can use machine learning for. With machine learning, the computer isn't told the meaning of these dimensions, it just sees them as numbers. And it sees each set of numbers as a data point. But by looking across all of these dimensions at once, it's able to place related points closer together in high-dimensional space.
Here's a concrete example where words are treated as high-dimensional data points. The important thing to remember is that we haven't told the computer the meaning of words. Instead, we've shown it millions of sentences as examples of how words get used. Here's a visualization of the results. We're looking at a subset of words that the computer has learned about. Each dot represents one word. Each word is a data point with 200 dimensions. Using a technique called t-SNE, the computer clusters words together that it considers related, and clusters form based on meaning, even though we've never taught it the meaning of words. Here is a cluster of numbers, months of the year, words related to space, people's names, cities, and so on.
We can also look closely at smaller sets of words. If we search piano, we can run t-SNE only on words related to piano. We get clusters of composers, genres, musical instruments, and more.
And this approach doesn't just work for words. For example, you can also treat an image as a high-dimensional data point. Here's a data set where lots of people wrote digits between 0 and 9. People write in all kinds of ways. So the question is, instead of us needing to manually code rules for all the ways people write, could a machine figure it out itself using machine learning? Each image is 784 pixels. The computer treats each pixel as a dimension. Again, using t-SNE, it clusters these images in a high-dimensional space. We've color-coded them so that it's easier for us to see what's going on. And you can see groups of digits clustering together. It's learned something about the meaning of these digits.
These visualization techniques we've been exploring can be useful for all kinds of things. That's why we're working on open sourcing all of this as part of TensorFlow, so that anyone can use these tools to explore their data.
Sorry. So some really cool stuff going on here. Lots of visualizations, but also lots of ways to analyze data in order to help machines learn, which of course is this whole section of modeling, right? So there are 4 links here that I do want you to click on, and I'm going to show them briefly because I want to make sure we have time for everything in here. We can always come back to it. But the first one is 100,000 stars. And what this is this is a visualization of starting with our sun. There's our sun. And then zooming out. And now we see the solar system, right? And we zoom out, we see the orbit of Neptune. And then we see our solar system shrinking down. And as we zoom out, we start to see what 1 light year is. That's the amount of distance that light travels in 1 year. And then we see after 1 light year, we start to see some stars. This is the closest star to our sun, Alpha Centauri. And we start to see more and more stars, and you know, the really cool part about this is that we can grab this and drag it and rotate and start to see this in 3 dimensions. So this visualization allows us to see the relative positions of these stars to each other, all right, especially as we zoom out. And there's a reason that all of these stars are different colors. It has to do with their relative heat, as you see on the scale in the upper left-hand corner. And now we take an even bigger view. Go ahead, Ayana.
I was wondering what the colors meant.
Yeah, so cooler stars are on the reddish side. Warmer stars are on the bluish purplish side. Our sun is right about here. So it's an average star.
Hot. I mean, not hot, but like it's a lot of cool and hot stars.
Yeah, and it depends on where in the life cycle the star is. I don't want to get into astronomy too much because it's not really within the scope of this visualization. But as we zoom out, you start to see that there's a cluster of stars, right?
Right.
And we can still manipulate it, and we go, wait a minute, what? Huh? What's that then? Well, that's the Milky Way. All right, we are in the Milky Way, but we're on a spiral arm of the Milky Way. We're not even in the middle of the Milky Way. So to give you some context, this entire visualization is taking into account about 400 billion stars. The 400 billion stars that are in this area, okay? And this area of the Milky Way having billions and billions of clusters itself. And then think about the billions and billions of galaxies that exist within the universe, and it's pretty mind-blowing. All right, so this helps to give some perspective of the enormity of not only the Milky Way galaxy, but the enormity of just our little tiny part of the Milky Way galaxy and the universe itself. All right, without this visualization, it's almost impossible to conceptualize.
Yeah, because, you know, when we're talking about, you know, I feel like it's easier to, like, when you have a visualization in front of you, it's easier to, like, you know, understand it and comprehend that it is, you know, real and happening.
And that's probably the most important thing to take away from this, is that if you can learn how to do this three-dimensional modeling, you can make things real for people, right?
Okay.
And it's a wonderful, not only teaching tool, but it's a wonderful way of being able to entertain, all right, as we're gonna see at the end of this. So here are what are called wireframes. And so this is a cylinder, right? It's a very simple cylinder, and all we're seeing are the lines that define the cylinder. By defining those lines and those points, then in this particular 3D visualization, then what we can do is we can manipulate it, turn it around, spin it, and all of these points can be re-rendered by the graphics engine that's running this in order to give us this illusion of three-dimensionality. But make no mistake, I can leave it there, and if I'm not moving it and you don't actually manipulate it at all, then it's completely two-dimensional. All of this is obviously two-dimensional. This is not holographic. Your brain is turning it into 3 dimensions by adding this extra piece of motion, all right? And so this is how a wireframe works. Now, if we add things to the wireframe, then you'll see that, in fact, we're able to add dimensionality through other techniques. But you know, this particular set of visualizations allows us different sorts of geometries. This is the torus, aka donut. All right. This one, I was just fooling around with a variety of different animations. This is the mirror animation. So this is a mirror visualization right here, and there's a mirror right here, and you can manipulate it so you can see from above what it looks like. You can see from the side. You can even look from below, right, as if you're in the mirror itself. Literally, you could spend hours looking through these different visualizations. The third one I wanted to show you is the teapot, okay? So we can look at it as a wireframe, and in order to understand the rest of what we're going to talk about today, it's important to understand that this is how three-dimensional visualizations or three-dimensional objects are created, is through a wireframe, through a bunch of lines that end up defining what are called polygons. And you know, polygons from geometry are objects that have X number of sides. All right, any number of sides and determined in any sort of way. But basically, this teapot is made of thousands of polygons. How those polygons interact with each other defines the behavior of the object or the shape of the object as you move it through three-dimensional space. And then you can layer on top of it a flat shading. And then we can change all sorts of characteristics of not only the material, but the lighting. So we can make the material really shiny, okay? And it doesn't look shiny yet because of how we're lighting it. We can increase the lightness of the lighting, and that will bring out some of the shininess. All right, we can saturate it, we can change the color of our lighting, and we can also change the color of the actual material. All right, you can play around with all of these things and see how it influences. We can change where the light's coming from. on the x-axis, on the y-axis, and on the z-axis. Z-axis is depth, y-axis is up and down, x-axis is left and right. Play around with some other textures, and when you make it smooth, then that's, I don't know, I feel like that's really satisfying. And what this is doing is it's smoothing out the light on all the polygons so that you don't see any rough edges. Glossy introduces this texture that reminds us of particular materials. And then we can change how much light is falling on this glossy texture, and thereby changing how it behaves. This textured, this allows us to actually see, take a look behind the scenes a little bit on each polygon to see how it's reacting. And then of course there's the reflective, which is my favorite, where there's a scene that's surrounding it, right? And that scene is being reflected in the object itself. It's totally my favorite of all these. You see that looks like an iPhone at the bottom, right?
Do you think that when, like, you know the part that you did before you got to the reflective piece?
This one?
Yeah. Do you think that's the image is like the pre-learning of where the images are gonna go? Or is it like the colors, like, I don't know.
This is the mathematical calculations that are being done as far as how reflective, what hue is on each polygon, so that you can take a behind the scenes look to see how this is actually done. And we can even zoom in and see the intricacy of some of these polygons. That at the top, the polygons need to get super skinny. And then along the side, they're almost like squares or rectangles.
Right.
Right. So you have to strip away the three-dimensionality in order to understand what's going on here. Don't think of this as a square that's being stretched. Think of it as a polygon that has a shorter top and a longer bottom. All right, exactly how you see it. Like,
Right.
you could trace this out, and it's two-dimensional. It just that it gets manipulated as we move it through three-dimensional space, so that that polygon has different measurements as it gets manipulated. All right. So, questions about this? I know it's a lot.
That's my main question. It's really cool. And it's crazy that all this work goes into making a little teapot.
Right? Look at that. Just hovering into space, and I can zoom in on it, and then we see different reflections, right? Now,
Yes.
now this is pretty cool, right? This gives you the foundations of how, like, modern gaming is done. This gives you the foundations of how CGI for movies is done.
Okay.
All right, but I'm not going to leave it at that. I want to give you more information about how this is actually done. Before we get there, I want to make sure that we understand how you might be asked about this on the EA. So first of all, think about how you would answer this question. Outline a situation where 2D visualization would be more appropriate than 3D visualization. So what do you think? When would you want to use 2D over 3D?
I'd probably say like planning in a way, like construction, you know, like when they're like making a, you know, like the first, like, you know, like house plans, like that.
Yep. Architectural plans?
Yes.
Yeah. I agree. It's less expensive to do it, right? You can just sketch it out. You don't actually need to see it in 3 dimensions. Most people who look at house plans can visualize what it's going to be.
Yeah.
Right? So even simpler, a map. A Google map does not need to be 3 dimensions, but there is Street View, right?
Mm-hmm.
That Street View is 3 dimensions. It is a 3-dimensional visualization of what an area looks like. And that part is helpful for finding the particular house, right? You don't need the you don't need the Street View for the 500 miles between Cleveland and New York City. You need the Street View for the house in Manhattan that you're visiting, because you want to see what it looks like so that you know exactly where you're going. So the map showing the journey doesn't need it, but maybe that last piece does. The route just needs to be shown on a phone. The 3D version, it's going to take up a lot of space, and in the case of a phone, it's going to take up a lot of bandwidth. So if you're trying to visualize the entire way from Cleveland to New York City, that's going to take a lot of space on the phone, or it's going to take a lot of space on the internet, and it's going to suck up all your data, or it's going to cause your phone to lose battery life too quickly. All right, the internet connection might be too slow. So there's all sorts of things to consider, 2D over 3D. Basically, it comes down to 3D when you can do it, 2D when it doesn't make sense in terms of cost or time. All right, so let's take a look at another question here. Artist is planning to create a statue but decides to do some planning before she starts. What would be the advantages to the artist of using a computer-aided design or CAD program and graphic processing software for 3D modeling instead of a series of sketches drawn by hand to experiment with designs? Have you guys ever used SketchUp? Google SketchUp.
No.
All right, it is the
Is it a different kind of Google ketchup?
so it is computer-aided design that Google gives away for free.
Oh, that's cool. A lot of things I haven't known about Google.
I just want to get in here just to give you a flavor of what it is capable of doing. So this would be this up here. Obviously, this is like layering a real video on top of it, all right? But this up here would be the actual, what you could do in SketchUp. You could throw a real landscape in here and then create your 3-dimensional architectural design on top of it in order to get a good visualization for how it works. And I wouldn't put it past SketchUp to actually be able to layer a video on top of that as well within the program. But this is the general idea. And then you would be able to manipulate this. You could walk into rooms. You could see this from all the different angles. You can see how the light plays with all the design over the course of a day by changing the light source. It's super powerful. So computer-aided design is, it's something that's been used. It's something I learned how to use in high school. It's been around for a long time, but it gets more and more sophisticated as time goes on. So what would be the advantages of this artist who's going to create the statue of using CAD and graphic processing software instead of a series of sketches drawn by hand to experiment with designs? What do you think?
What do I think about the method?
Yeah, what would be the advantages of using CAD and graphic processing software for 3D modeling?
You can get more of a realistic view, and also you can plan out more what you're gonna be using for this project to happen and stuff.
So Zainab, I disagree with you. So Ayana, I agree with you. Zainab, I disagree with you saying wouldn't take long to design. It's quick. That's actually one of the disadvantages of CAD if you're not familiar with it. okay? If, as an artist, you sketch something really quick, I know if I'm building something that it's really quick for me to sketch something, but it's going to take me a lot longer to develop it in CAD, all right? So there are other advantages, right? As far as time, the changes could be easily made and the effect of the 3D shape from other angles seen immediately. So as far as making changes, it would be easy. It wouldn't take as long to make changes, but it would take a lot longer to develop the thing itself. So there is a trade-off here of time and resources. You can easily undo a change to the model. It's a lot harder to erase a part of the sketch and then redraw that, right? And also it's the number of angles. With a 3-dimensional model using CAD or other graphic processing software, you can quickly and easily manipulate that model to see it from all those different angles. You can also scale the design. So if you're making the statue and you're like, okay, this is gonna be a 6-foot statue, and then the city comes along and says, yeah, we contracted you to make this 6-foot statue, but you know what? We really only have the money and the space to make it a 4-foot statue. You go, oh, no problem. I made it in CAD. I'll just change the scale and I'll make it a 4-foot statue. And maybe your sketch took into account 6 feet and how it would look, and you're like, oh man, I have to redo these sketches. But if you're doing the 3D visualization, you don't have to redo the sketches, you just change the scale. So there's lots of advantages to doing it, but it does take more time and it costs more generally. Oh, I forgot this last one. CAD files are less likely to get damaged. So 3D visualizations are constructed from a mathematical representation of the object, like this polygon, right? We're using geometry in order to represent objects. The objects are then what is called rendered into 3D models. And so all of this math has to be applied, and we're talking like millions of instructions per second, right? Of figuring out what this polygon looks like from this angle, what the light looks like when it reflects off of it, what the color looks like in this particular situation. All of those things are done mathematically. Only the face of the object you're viewing is visible, and as the object starts to turn or move, the face you're about to view starts to be rendered. So we're not going to render, we're not going to calculate any of the light, any of the polygons that we can't see. We're only going to calculate the ones that we can, in general, in order to save memory. But 3D visualizations are incredibly memory and CPU intense. The more complex the model, the more computational resources like CPU and memory are required to render that visualization. So here's what the process of rendering is like. First, you apply light and texture to a model. You can use techniques like ray tracing. We're going to get into all these. The ray tracing is applied to this wireframe 2D representation. Remember, we saw the wireframe over here. And this produces this realistic view of the final product in the chosen material. And let's take a look right now. Tell you what, this is, I believe this is the big one. So I do not want to try to stream this over Zoom for you, because any hiccups in my bandwidth or in yours will make this a not pleasurable and not useful experience. So here's what I'm going to ask you to do is to view it on your own. Do both of you have the link for the YouTube video off the presentation? Or can you view the video on your own? Okay, Zainab says yes. Ayana?
Yeah.
Okay. If, for the sake of bandwidth, you need to log off of Zoom and then come back on after the video, that's fine. If it's loading just fine and you can keep Zoom on in the background, then do that. But what I'm going to do, all right, let's give this a shot. Are both of you on Slack?
I'll need to log in real quick.
So here's what I want to do is I'm actually gonna stop the Zoom for a minute, and then while the video is going, we'll chat via Slack about it. And that should make sure that you don't have any hiccups in the video itself. It's because it's like 17 minutes long, and so I don't want to try to do this over Zoom. So once you're on Slack, go to the CSHL channel. I just tagged you guys. We'll make sure we're all set on Slack. I posted the YouTube video to Slack as well.